Welcome. Tonight, we're not crossing oceans or continents. We're venturing into the cosmos. Prepare to have your sense of reality challenged as we explore the universe's strangest secrets. From invisible matter to places where time bends, these are not fantasies, but the true fabric of existence. Let's peel back the veil and witness the weird, magnificent nature of our universe. This is a voyage to the edge of understanding. Let's begin. Take a moment. Look up at the night sky on a clear, dark night far from city lights. What do you see? All that light, those twinkling stars, the celestial tapestry above? It seems like so much, doesn't it? But in reality, it's just a sliver, a tiny fraction of what's truly out there in the vast expanse of the cosmos. Most of the universe, about 85%, an overwhelming majority, is made of something we call dark matter. It's invisible, undetectable by our current instruments, yet absolutely essential to the structure and evolution of the universe. We know it's there, even though we can't see it directly, because galaxies spin too fast, much faster than they should based on the amount of visible matter they contain. There simply isn't enough visible matter, like stars and gas, to provide the gravitational pull needed to hold these galaxies together at such high speeds. Dark matter acts as a cosmic scaffold, an invisible framework upon which the visible universe is built. It plays a crucial role in shaping galaxies, influencing their size, shape, and distribution. It's the invisible glue that holds galaxy clusters together, preventing them from flying apart and ultimately holding the entire universe together. Scientists are on a relentless hunt for it, conducting experiments in deep underground labs, shielded from all other forms of radiation. But so far, despite their best efforts and sophisticated equipment, dark matter remains elusive, a cosmic mystery waiting to be solved. Imagine the universe as an ocean, vast and deep, filled with all sorts of wonders. The stars, the galaxies, all the visible matter are like the fish swimming in that ocean, beautiful and fascinating. But dark matter is the water itself, everywhere, surrounding everything, an invisible medium that shapes the cosmic landscape. Unraveling its mystery, understanding what dark matter truly is, could rewrite our understanding of matter itself, and revolutionize our understanding of the universe. The universe is filled with wonders, but some places defy our everyday understanding of reality, places where the familiar laws of physics seem to bend and break. These are the realms of black holes. Mysterious and powerful, they represent the ultimate frontier of our knowledge. Born from the cataclysmic collapse of massive stars, marking the end of their stellar lives in spectacular supernova explosions, they concentrate an unimaginable amount of mass into an infinitesimally small point, a singularity, a place where matter is crushed beyond comprehension. The gravitational pull is so intense that nothing, not even light, can escape its grasp, creating a boundary known as the event horizon. The event horizon marks the point of no return. Cross it, and you are forever lost to the black hole's embrace. These cosmic behemoths warp the very fabric of space and time to unimaginable extremes, creating distortions that challenge our understanding of the cosmos. Near a black hole, time slows dramatically due to the intense gravity. Reality itself is twisted into something almost unrecognizable, a testament to the power of these objects. Once just a theoretical prediction derived from Einstein's equations, a concept confined to the realm of theoretical physics, we've now directly detected their existence through the gravitational waves they generate, ripples in the fabric of space-time itself. We have even managed to capture an image of a black hole's shadow, a groundbreaking achievement that confirmed their existence and provided invaluable data. These cosmic giants play a crucial role in shaping the structure and evolution of galaxies, influencing the distribution of stars and gas across vast distances. They recycle matter, drawing in surrounding gas and dust into swirling accretion disks, feeding the black hole and releasing tremendous amounts of energy. Black holes push the limits of our understanding of physics, forcing us to confront the most fundamental questions about gravity, space, and time. At their core, within the singularity, our current understanding of the universe breaks down, leaving us with more questions than answers. Black holes are not just cosmic objects, they are gateways to the unknown, where science meets the very edge of what we can comprehend. Now, let's shrink to the quantum realm, where reality gets truly bizarre. Quantum entanglement links particles so that a change to one instantly affects its partner, no matter the distance. Einstein called it spooky action at a distance, and experiments prove it's real. This phenomenon is the foundation for quantum computing and cryptography. Entanglement challenges our ideas of space and separateness, hinting at a universe more interconnected than we ever imagined. At the quantum level, distance may be an illusion. The universe is stranger and more unified than it appears. When massive stars die, they sometimes leave behind neutron stars, cosmic pressure cookers. These city-sized objects pack more mass than our sun into a sphere just 20 kilometers wide. A teaspoon of neutron star material weighs billions of tons. Their gravity is so intense, matter is crushed into pure neutrons. Many spin rapidly, emitting beams of radiation, pulsars, the universe's lighthouses. Neutron stars are natural labs for studying matter at its most extreme. They reveal the fate of stars and the limits of physics. Imagine pointing a highly sensitive radio telescope towards what appears to be an empty patch of sky, far away from any stars or galaxies. What would you expect to find? Surprisingly, you'll detect a faint, almost uniform microwave glow permeating the entire cosmos, the oldest light in the universe, a relic from a time long before stars or galaxies even existed. This is the cosmic microwave background, or CMB for short. It's not just any ordinary radiation, it's the afterglow of the Big Bang, the event that birthed our universe as we know it. The CMB provides us with a snapshot of the universe in its infancy, when it was just 380,000 years old. That's the moment when the universe had finally cooled down enough for atoms to form, allowing light to decouple from matter and travel freely through space for the first time. Before this, the universe was a hot, dense plasma where light was constantly scattered. Over the ensuing billions of years, as the universe expanded at an accelerating rate, this primordial light stretched out, its wavelengths increasing until it shifted into the microwave part of the electromagnetic spectrum. This stretching, known as redshift, is a direct consequence of the universe's ongoing expansion. Now, if you look closely at the CMB, you'll notice tiny temperature fluctuations, minute variations in the background radiation. These seemingly insignificant fluctuations are incredibly important because they represent the seeds from which all the cosmic structures we see today, galaxies, clusters of galaxies, and vast cosmic voids, ultimately grew. The CMB is therefore both a fossil, a remnant of the early universe, and a blueprint containing the instructions for how the universe would evolve. It's a treasure trove of information, revealing crucial details about our universe's earliest moments and its fundamental properties. By studying the CMB, we're essentially looking back in time, getting as close as we possibly can to witnessing the very birth of everything. Time feels constant, but Einstein showed it's flexible, warped by speed and gravity. The faster you move, the slower your time passes compared to someone at rest. GPS satellites prove this daily. Their clocks tick differently due to their speed and weaker gravity. Near massive objects like black holes, time slows dramatically. There's no universal now. Each observer experiences time uniquely. Time dilation forces us to rethink past, present, and future. In our universe, every clock ticks to its own cosmic rhythm. Now, the most mind-bending idea. Our universe may be just one of many. The multiverse theory suggests countless universes, each with different laws of physics, may exist. Some theories, like eternal inflation, predict new universes are constantly forming. Most would be inhospitable, but a few, like ours, might support life. This could explain why our universe seems so perfectly tuned for existence. We have no direct evidence, but the possibility expands our cosmic perspective. The multiverse reminds us, even our universe may not be the center of everything. We've glimpsed the universe's greatest mysteries, from dark matter to the multiverse. Which secret surprised you most? Share your thoughts below. If your curiosity was sparked, subscribe for more cosmic journeys. The quest for knowledge never ends. There's always more to discover. Until next time, keep wondering, keep exploring, and stay curious.
Have you ever gazed at the night sky and wondered where it all began? Our sun is just one of hundreds of billions in the Milky Way itself, one of billions of galaxies. This cosmic expanse raises a timeless question. How did the universe begin? For millennia, humans have sought answers first through myths, now through science. Today, we use physics and telescopes to peer back in time, uncovering a story as epic as any legend. The laws that govern our world, the atoms in our bodies, all trace back to the universe's birth. By studying the cosmos, we study our own origins. We are, quite literally, stardust. So let's journey back to the very first moments of existence, before stars, before galaxies, before even time as we know it. We'll explore the leading explanation for our cosmic origins, the Big Bang Theory, the story of everything from almost nothing. What is the Big Bang? Simply put, it's the idea that the universe began as an incredibly hot, dense point. It wasn't an explosion in space. Space itself began expanding. About 13.8 billion years ago, everything, matter, energy, space and time, emerged in a single moment. Imagine all the universe compressed smaller than an atom, then expanding rapidly. This expansion was smooth and uniform, like a balloon inflating. As the universe grew, it cooled, allowing the fundamental forces and first particles to form. The Big Bang Theory doesn't explain what came before or what caused it. It describes what happened after that first instant. The conditions at the very beginning are still beyond our current physics, but from that hot, dense state, the universe evolved into the vast cosmos we see today. The Big Bang happened everywhere at once, including right where you are now. There was no outside. The universe is all there is. Every point in space was once part of that singularity. We are living in the aftermath of that primordial event. Let's zoom in on the universe's first moments. In the tiniest fraction of a second, the universe was a seething soup of energy, hotter than anything we can imagine. The four fundamental forces were likely unified, then gravity split off as the universe expanded. Next came inflation, a burst of exponential growth, smoothing out the cosmos. After inflation, the universe was still hot and dense, filled with fundamental particles. As it cooled, quarks combined to form protons and neutrons, the building blocks of atoms. In the first few minutes, these fused into hydrogen and helium nuclei. For hundreds of thousands of years, the universe was a glowing, opaque fog. Light was trapped, unable to travel freely. Only when the universe cooled enough for electrons to join nuclei did atoms form. Suddenly, light could travel, marking the universe's first transparency. This ancient light still fills the cosmos today. The stage was set for stars and galaxies to form. How do we know this story is true? The Big Bang Theory stands on powerful evidence. First, the universe is expanding, galaxies are moving away from us, and the farther they are, the faster they recede. This fits perfectly with an expanding universe. Second, the cosmic microwave background, or CMB, is the afterglow of the early universe, ancient light released when atoms first formed. This faint microwave radiation fills the sky and matches Big Bang predictions exactly. Third, the abundance of light elements, hydrogen, helium, and lithium, matches what we'd expect from a hot, dense beginning. These elements were forged in the universe's first minutes. Finally, tiny ripples in the CMB became the seeds for galaxies and clusters. Gravity amplified these small fluctuations, shaping the cosmic web we see today. The structure of the universe, from stars to vast clusters, is a direct result of these early conditions. All these clues point to a hot, expanding origin. The evidence is written across the cosmos. The Big Bang Theory is the result of many brilliant minds. Einstein's general relativity laid the groundwork, suggesting a dynamic universe. Alexander Friedmann and Georges Lemaitre used these equations to propose an expanding cosmos. Lemaitre imagined a primeval atom, the universe's starting point. Edwin Hubble provided the observational proof galaxies are moving away, confirming expansion. In the 1940s, George Gamow and Ralph Alpha predicted the universe's light element abundances and a lingering afterglow. Decades later, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, the Big Bang's smoking gun. Each discovery built on the last, transforming a bold idea into a robust scientific theory. The Big Bang became the leading explanation for our cosmic origins. It's a story of theory, observation, and serendipity. Science is a team effort spanning generations. Our understanding continues to grow. The name Big Bang wasn't meant as praise. British astronomer Fred Hoyle, a critic of the theory, coined it as a term of ridicule. He favoured the steady-state model, believing the universe was eternal and unchanging. On a 1949 radio broadcast, Hoyle mockingly called it "this Big Bang idea." Ironically, the name stuck. Short, catchy and memorable. Despite its misleading image of a noisy explosion, Big Bang captured the public's imagination. Scientists eventually embraced it, recognizing its power as a communication tool. The name reminds us that science is shaped by debate, rivalry, and even accidental branding. Hoyle never accepted the theory, but his nickname became iconic. Sometimes a simple phrase can define an entire field. Our journey to understand the universe's beginning is far from over. The Big Bang Theory explains much, but mysteries remain. Most of the universe is made of dark matter and dark energy, unknown and unseen. Scientists are searching for clues about these cosmic ingredients and the universe's earliest moments. The period of inflation, for example, is still being tested. New telescopes and experiments may soon reveal more about our origins. The quest continues, driven by curiosity and wonder. Every discovery leads to new questions. We are all part of this grand adventure. Keep looking up, keep asking. The cosmos is calling. When you look up at the night sky, you see a faint river of light, the Milky Way. For centuries, we thought it was just a cloud, but it's actually our home galaxy, a vast city of stars, dust, and gas bound by gravity. Our sun is just one of hundreds of billions of stars in this immense structure. Galaxies are the universe's building blocks, cosmic islands floating in the void. They're not static. Galaxies are born, grow, collide, and evolve. Stars are born in fiery nurseries and die in supernovae, spreading elements needed for planets and life. There are at least 2 trillion galaxies in the observable universe, each unique in shape and size. Spirals like the Milky Way, massive ellipticals, and chaotic irregulars fill the cosmos. The scale is staggering. If the sun were a grain of sand, the Milky Way would be a beach stretching for thousands of miles. And that's just one galaxy among trillions. This cosmic tapestry, woven from starlight and gravity, extends in every direction. It's a humbling perspective. Our world is a tiny part of a much grander story. The universe's history is written in the light of distant galaxies. We're only beginning to learn how to read it. Galaxies remind us how small we are, yet how connected to the cosmos. The story of galaxies is the story of the universe itself. Not all galaxies fit neat categories. Some are cosmic oddities that challenge our understanding. The Sombrero Galaxy, for example, has a bright core and a thick dust lane, resembling a celestial hat. Its dust ring is a hotbed of star formation, contrasting with its calm, ancient core. The Antennae galaxies are 2 galaxies colliding their tidal tails, stretching out like insect antennae, a preview of the Milky Way's future collision with Andromeda. Centaurus A looks like a normal elliptical galaxy, but radio telescopes reveal jets of plasma blasting from its core, powered by a supermassive black hole. There are galaxies with polar rings and jellyfish galaxies trailing gas as they move through clusters. Each oddity is a puzzle, revealing new cosmic behaviors. These strange galaxies force us to rethink what's possible in the universe. They're the exceptions that expand our understanding. The universe is a zoo of wonders, and we're just beginning to explore its strangest exhibits. Every odd galaxy tells a story of cosmic creativity. The Cartwheel Galaxy stands out as a cosmic bullseye, an extraordinary ringed structure 500 million light-years away. Once a normal spiral, it was transformed by a smaller galaxy plunging through its center like a stone dropped in a pond. The impact sent a shockwave outward, triggering a burst of star formation in the outer ring. The bright blue ring is filled with young, massive stars, while the inner core holds older stars. Faint spokes connect the ring's remnants of the original spiral arms. The Cartwheel is a rare snapshot of galactic transformation in action. It's a laboratory for studying high-speed collisions and starbursts. The galaxy's structure will keep evolving for millions of years. The Cartwheel reminds us that the universe is dynamic, often violent, and capable of breathtaking beauty. Even chaos can create cosmic masterpieces. Hoag's object is a cosmic enigma, a perfect blue ring of young stars encircling an older yellow core with an empty gap in between. Discovered in 1950, its origin remains a mystery. Some think it's a ring galaxy formed by an ancient collision, but there's no evidence of a culprit nearby. Others suggest it was once a barred spiral, but the perfection of the ring defies easy explanation. The core and ring rotate at nearly the same speed, adding to the puzzle. Hoag's object challenges our models of galaxy formation. It's a beautiful anomaly, reminding us how much we still don't know. The universe isn't obliged to make sense to us. Some wonders simply refuse to fit our expectations. We can't visit distant galaxies, but we can see them thanks to powerful telescopes. The Hubble Space Telescope revolutionized our view, capturing sharp images of galaxies like the Cartwheel and Hoag's object. Hubble's deep field images revealed thousands of galaxies in tiny patches of sky. But visible light is just part of the story. Radio telescopes show us cold gas and black hole jets. Infrared telescopes like Spitzer and James Webb peer through dust to reveal newborn stars. The James Webb Space Telescope can look back to the universe's earliest galaxies. By combining data across the spectrum, astronomers piece together the life stories of galaxies. Each wavelength reveals a different chapter. Our instruments are our eyes on the cosmos, turning faint smudges into detailed portraits. Technology lets us explore the universe from afar. With trillions of galaxies, each with billions of stars, the question arises, are we alone? The elements for life are forged in stars and scattered across galaxies. Planets are common, orbiting most stars we observe. But strange galaxies complicate the search for life. Starbursts and supernovae may make some regions hostile. Quiet galactic suburbs like ours might be best for complex life. Yet, alien environments could host life forms beyond our imagination. The Fermi paradox asks, if life is common, why haven't we found it? Maybe life is rare, or distances are too vast for contact. Studying galaxies helps us focus our search for habitable worlds. The universe's silence only deepens the mystery. Our journey through the cosmos always leads us back to Earth, a pale blue dot in a vast universe. Studying strange galaxies highlights the fragility and uniqueness of our home. In a universe of chaos, we live in a rare oasis of stability. This perspective inspires humility and wonder. The iron in our blood and the calcium in our bones were forged in ancient stars. Our curiosity drives us to explore, to seek answers beyond the next star. Galaxies are the continents of the cosmic wilderness. Their light carries secrets of evolution, gravity, and our own origins. Deciphering these messages is a grand adventure. Looking outward helps us reflect inward on our place in the cosmos. The universe's strangeness expands our sense of wonder. The journey to understand it is just beginning, and every discovery brings us closer to the heart of the cosmic story. Come with me on a journey, not across land or sea, but through time itself. Our story begins 13.8 billion years ago, when everything was compressed into a single, unimaginably dense point. Then, in a flash of energy, the universe began, the Big Bang. This was the birth of time, matter, and the laws of physics. The universe expanded and cooled, forming the first particles, protons, neutrons, and simple atomic nuclei. For hundreds of thousands of years, the cosmos was a hot, dense fog where light was trapped. But as the universe cooled, electrons joined nuclei to form the first atoms, mostly hydrogen and helium. Suddenly light was free to travel, and the universe became transparent. This ancient light, the cosmic microwave background, still echoes across space today, a baby picture of our universe. With the fog lifted, the universe entered the cosmic dark ages. No stars, just vast clouds of gas. But these clouds weren't uniform. Tiny fluctuations in density became the seeds of everything to come. Gravity began its patient work, pulling denser regions together. These small differences would shape the future, setting the stage for the first stars and galaxies. The universe was no longer a blank canvas, but a place where structure could emerge. From this darkness, the next chapter of cosmic creation was about to begin. The story of everything was underway. The universe, once a hot, uniform fog, was now primed for transformation. The first lights were about to flicker on, and with them, the cosmos would never be the same. The journey of creation had truly begun. Gravity gathered gas into swirling clouds nebulae, the universe's first nurseries. Deep inside, pressure and temperature soared until hydrogen atoms fused, igniting the first stars. These giants burned hot and bright, ending the cosmic dark ages. They lived fast, died young, and exploded as supernovae, briefly outshining entire galaxies. In their fiery deaths, stars forged new elements: carbon, oxygen, iron, the building blocks of planets and life. These elements were scattered into space, enriching the cosmos for the next generation of stars. The universe was no longer just hydrogen and helium. It was becoming more complex, more interesting. Each stellar death seeded the cosmos with the raw materials for worlds like our own. The cycle of birth and destruction made the universe richer with every generation. The first stars lit up the darkness and set the stage for everything to come. From their ashes, new stars and planets would form. The universe was learning to recycle, to build, to evolve. The cosmic story was accelerating. As stars ignited, gravity pulled them together into vast spinning galaxies, cosmic cities of light. Early galaxies were chaotic, colliding and merging in spectacular dances. Over time, these interactions shaped the beautiful spirals and ellipticals we see today. Our Milky Way is one such spiral, home to hundreds of billions of stars and a supermassive black hole at its center. Galaxies cluster together, forming a cosmic web separated by immense voids. This structure grew from tiny fluctuations in the early universe, amplified by gravity. The universe became a tapestry of light and darkness, order and chaos. But this process of creation cannot last forever. The universe is still expanding, and its fate depends on that expansion. The next chapter takes us into the unknown. For decades, we thought gravity would slow the universe's expansion, but in the late 1990s, astronomers discovered something shocking. The expansion is speeding up. A mysterious force, dark energy, is pushing space apart, overwhelming gravity. We don't know what dark energy is, only that it's accelerating the universe's growth. The more space expands, the faster it expands, a runaway effect. This changes everything. The cosmos is not coming together, but drifting apart. In the far future, distant galaxies will vanish beyond our reach, leaving only our local group. The night sky will grow emptier, lonelier. The universe's fate is now driven by this strange, invisible force. The final acts of the cosmos are set in motion. If dark energy continues, the universe faces the big freeze, a slow fade into darkness and cold. Over trillions of years, star formation will cease as gas runs out. The last stars, dim red dwarfs, will flicker out, leaving only stellar remnants. White dwarfs, neutron stars, black holes. Even black holes will eventually evaporate through Hawking radiation, vanishing over unimaginable timescales. Matter may decay, dissolving into a thin, cold soup of particles. The universe will become a vast, empty void, approaching absolute zero. No new stars, no new worlds, just silence. This is the quiet end, a universe run down with nothing left to happen. The story of creation closes in darkness, but other endings are possible. If dark energy grows stronger, the universe could face the Big Rip. Galaxies, stars, planets, even atoms would be torn apart as space itself unravels. The end would come swiftly and violently, destroying all structure. Alternatively, if gravity wins, the universe could collapse in a big crunch. Everything would rush together, ending in a fiery singularity. Some imagine this could spark a new Big Bang, a cosmic rebirth, the Big Bounce. But with accelerating expansion, these scenarios seem unlikely. For now, the evidence points to a one-way journey into cold and dark. The universe's fate remains one of science's greatest mysteries. Yet the search for answers continues. We've traveled from the birth of time to the universe's possible ends. A cold fade, a violent rip, or a fiery crunch. This cosmic story can make us feel small, but our ability to understand it is what makes us significant. We are stardust, conscious matter, the universe aware of itself. Our curiosity drives us to explore, to question, to seek our place in the cosmos. Science is our tool for discovery, connecting us to everything around us. By looking up, we find wonder, humility, and perspective. The universe's story is our story. Its beginning, our beginning. Its fate, our context. Studying the cosmos teaches us about ourselves and the preciousness of our world. The universe doesn't owe us understanding, yet we are beginning to grasp its secrets. That journey is worth taking. Look up at the night sky. You see stars, planets, galaxies, a dazzling display of light. For centuries we believed this visible universe was all there was, but the cosmos hides a deeper truth. Most of it is invisible. Everything we see, stars, planets, gas, dust, makes up less than 5% of the universe. That means 95% is missing from our view. This unseen majority is made of two mysterious things: dark matter and dark energy. They don't shine or cast shadows, but they shape the universe on the grandest scales. Our familiar universe is just the tip of a cosmic iceberg. The quest to understand these invisible forces is a journey into the unknown, challenging our senses and our science. We're explorers at the edge of a vast, uncharted continent, just beginning to map its outline. The clues are faint: gravitational pulls, cosmic pushes. But they tell a story of a universe bound and driven by the unseen. This is the greatest detective story in science, one that could rewrite our understanding of space, time, and reality. The cosmos is calling us to look deeper, beyond the light. Let's begin our journey into the invisible universe. What keeps galaxies together? It's not just the stars and gas we see. When we measure how fast stars move in galaxies, especially at the edges, they're moving too quickly to be held by visible matter alone. They should fly off, but they don't. Something unseen is holding them in place. This was our first clue. There must be extra mass, invisible but powerful. We call it dark matter. It doesn't emit, reflect, or absorb light, completely invisible. We only know it's there because of its gravity. Dark matter acts as the cosmic glue, holding galaxies and clusters together. We see its effects everywhere, in galaxy rotations, in how clusters bend light from distant objects, a phenomenon called gravitational lensing. The mass we measure from these effects is much greater than what we see. Dark matter outweighs normal matter by about 5 to 1. Imagine a vast, invisible web stretching across space, with ordinary matter gathering in its densest knots. Galaxies form and evolve within these halos of dark matter. Without it, the universe would be a diffuse cloud. No galaxies, no stars, no us. Dark matter is the hidden framework of the cosmos. If dark matter holds the universe together, dark energy is pushing it apart. For decades, scientists wondered if gravity would slow the universe's expansion or reverse it. The surprise? The expansion is speeding up. Something is acting like anti-gravity, stretching space itself and driving galaxies apart faster and faster. We call this force dark energy. It's a property of space, a kind of energy that grows as the universe expands. Picture galaxies as raisins in rising dough. The dough expands and the raisins move apart. Dark energy makes up about 70% of the universe's energy. Its discovery means the universe's fate is likely a cold, lonely future, with galaxies drifting ever farther apart. Dark energy is the dominant yet least understood force shaping our cosmos. The hunt for dark matter began in the 1930s with Fritz Zwicky, who noticed galaxies in clusters moving too fast for their visible mass. He proposed dark matter, but his idea was ignored for decades. In the 1970s, Vera Rubin and Kent Ford found that stars in spiral galaxies moved too quickly at the edges, clear evidence of massive invisible halos. The discovery of dark energy came in the late 1990s. Two teams used supernovae to measure cosmic expansion, expecting to find it slowing down. Instead, they found it was speeding up. This shocking result turned cosmology on its head. The leaders of these teams won the Nobel Prize for revealing the universe's accelerating expansion. These discoveries opened a new era in our understanding of the cosmos. How do you study what you can't see? Scientists use clever, indirect methods. For dark matter, they map its gravitational effects with telescopes, watching how it bends light from distant galaxies. Underground, sensitive detectors wait for rare collisions with dark matter particles, WIMPs. At particle accelerators like CERN, physicists try to create dark matter in high-energy collisions, searching for missing energy in the aftermath. Studying dark energy is even harder. Astronomers map the universe's expansion with ever greater precision, using telescopes to track millions of galaxies and supernova. Missions like the Nancy Grace Roman Space Telescope will help chart dark energy's influence over time. By building detailed maps of the cosmos, scientists hope to uncover the true nature of these invisible forces. The search is painstaking, but every clue brings us closer. The universe's secrets are out there, waiting to be found. We know dark matter and dark energy exist, but their true nature remains a mystery. For dark matter, the leading theory is WIMPs, massive particles that barely interact with normal matter. But decades of searching have found nothing, so scientists consider other ideas like axions or even new laws of gravity. Dark energy is even more puzzling. The simplest idea is Einstein's cosmological constant, energy built into space itself. But calculations predict a value vastly larger than what we observe, a huge problem for physics. Maybe dark energy is a changing field, or maybe our understanding of gravity is incomplete. Proving any theory is incredibly hard. The effects are subtle and vast. We need precise measurements of the universe's expansion to solve these puzzles. For now, the universe keeps its secrets well hidden. Why chase these invisible mysteries? Because they make up 95% of reality. Understanding dark matter and dark energy is key to knowing the universe's fate and our place in it. The search drives innovation. We build the most sensitive detectors and powerful telescopes ever made. This quest pushes science forward, inspiring new technology and training future generations. Every great discovery in science has changed our view of the world. Learning what the universe is really made of could spark the next revolution in physics. So next time you look at the night sky, remember, the real story is in the darkness between the stars. Imagine the invisible web of dark matter holding galaxies together. Think of the mysterious energy pushing them apart. The cosmos is a grand mystery inviting us to explore and ask big questions. The answers are out there, waiting for us. The greatest discoveries are yet to come.
Since the dawn of consciousness, we have looked up, searching for meaning in the night sky. Our ancestors saw patterns in the stars, weaving stories to explain the unknown. This curiosity drove us from mapping constellations to building telescopes that peer back to the universe's origins. Each discovery revealed a cosmos more vast and mysterious than we imagined. The celestial dome became a solar system, then a galaxy, then billions of galaxies in an expanding universe. We now know we live on a fragile world, a pale blue dot, adrift in a cosmic ocean. Our maps have grown, but so have our questions. What lies beyond the horizon of our knowledge? Is there more beyond our universe? These questions, once the realm of myth, are now at the heart of modern physics. Our quest to understand the cosmos is a continuation of humanity's oldest story, the need to explore and find our place in the universe. The questions we ask about the stars are reflections of ourselves, our hopes, fears, and wonder. As we stand on the edge of understanding, we are still just beginning to grasp the true scale of existence. The journey continues, as it always has, with a single, persistent question: what's out there? Before we ask what's beyond the universe, we must define what the universe is. In cosmology, the universe is everything we can ever observe or interact with. All matter, energy, space, and time governed by the same physical laws. This is the observable universe, a vast sphere centered on us simply because we're the observers. Its boundary is set by the speed of light and the universe's age, about 46.5 billion light-years in every direction. This isn't a physical wall, but a horizon of information, the limit of what we can know. Beyond this, the universe likely continues, perhaps infinitely, with the same laws and galaxies. So, what lies beyond the observable universe? Most likely, just more universe. Our entire cosmic view is a tiny bubble in a much larger reality. But physics now asks an even bolder question. Could there be something beyond even this? Other universes? Other realities? The search for answers has led us to the radical idea of the multiverse. The multiverse is one of the most mind-bending ideas in modern physics. Imagine our universe as just one book in an infinite library. Each book a different universe with its own story and rules. This concept arises from theories like quantum mechanics and cosmic inflation. The many worlds interpretation suggests that every quantum event splits reality, creating countless parallel universes. Every choice, every possibility plays out somewhere in this branching web. Another path comes from inflation theory. The early universe expanded so rapidly that it may have spawned endless bubble universes. Each bubble could have its own physical laws, forever separate from ours. These universes are causally disconnected. No travel or communication is possible. The multiverse humbles us. Our universe, with its life-friendly laws, might be just one of countless experiments in a cosmic laboratory. Somewhere, the laws of nature could be wildly different, or nothing at all could exist. The multiverse challenges our sense of uniqueness and expands our imagination to the cosmic extreme. Are we just one story among infinite possibilities? Eternal inflation paints a picture of a primordial ocean, endlessly spawning new universes. Quantum fluctuations cause regions to stop inflating, releasing energy and creating bubble universes, ours included. Each bubble is an isolated island of space-time, separated by ever-expanding space. These universes are forever out of reach, causally disconnected for eternity. This theory may explain why our universe's physical constants are so perfectly tuned for life. If countless universes exist, each with random laws, it's no surprise we find ourselves in one that allows for observers. This is the anthropic principle. We exist because our universe permits it. Most bubbles may be lifeless or short-lived. Ours is simply one of the lucky ones. In the cosmic foam, we are a habitable bubble. By chance, not design. What if the universe is truly infinite, stretching on forever in all directions? In an infinite cosmos, every possible arrangement of matter must repeat. Eventually, there's another Earth, another you, somewhere out there. This is the quilted multiverse. Infinite space means infinite variations and infinite repetition. No new physics is needed, just the assumption of an endless, roughly uniform universe. Our observable universe is just one patch in an infinite cosmic quilt. Observations suggest our universe is flat, which, according to general relativity, implies it could be infinite. We can never see beyond our cosmic horizon, but the evidence points to a universe that may never end. The universe beyond our sight is likely just more universe, forever. This idea stretches back to ancient philosophers and is now supported by modern measurements. Infinity challenges our sense of uniqueness, but expands our sense of what's possible. In the endless cosmos, our story is just one among countless others. Are these ideas science? A theory must be testable, at least in principle. The multiverse was once pure philosophy, but now physicists are searching for indirect clues. One approach: look for bruises in the cosmic microwave background, evidence of past collisions with other universes. So far, no conclusive evidence has been found, but the search continues. Scientists also study the fundamental constants of nature. If they're not uniquely determined, it supports the idea of many possible universes. Experiments at particle colliders and studies of cosmic inflation may offer more hints. While we may never see another universe directly, each test refines our understanding. The quest itself pushes the boundaries of science and imagination. We stand at a remarkable moment, mapping the universe, yet realizing how much remains unknown. Theories of multiverses and infinite realms stretch our imagination and challenge our place in the cosmos. These are frontier ideas, not established facts. Some may be replaced by even stranger discoveries. The lack of answers is not failure, but an invitation to keep exploring. The search for what lies beyond touches our deepest hopes and sense of wonder. To contemplate the multiverse is to embrace infinity and possibility. We may never have a complete map of reality, but the journey itself enriches us. Our questions, our curiosity, define us as a species. Whether we are alone or one of countless universes, the act of asking is what truly matters. The cosmos whispers its secrets, and our greatest adventure is learning how to listen. For millennia and ages, humans have gazed up at the night sky, wondering always about our place in the cosmos and indeed its ultimate fate. Today, we confront the profound question, how will the universe eventually end? Let's explore the most astonishing, science-backed theories. Our first scenario, a potential fate for the cosmos, is the Big Freeze. Imagine a universe growing ever colder, sometimes referred to as heat death, a slow, chilling end where all energy dissipates. The universe is expanding at an accelerating rate, and dark energy, that mysterious force, is accelerating this process, pushing everything further and further apart. Over billions and billions of years, an almost incomprehensible span of time, galaxies will drift so far apart from one another, receding into the ever-expanding void. Their light, the very signals of their existence, will never reach us, lost to the vast distances. Star formation, the engine of cosmic creation, will cease as the available gas runs out, the raw material for new stars exhausted. Stars, the brilliant beacons of the universe, will eventually die, their fuel spent, leaving behind only stellar remnants. White dwarfs, the cooling embers of once great stars, neutron stars, incredibly dense and rapidly spinning, and black holes, the ultimate cosmic traps. These remnants, scattered throughout the expanding universe, will slowly cool and fade, radiating their remaining energy into the void, plunging the universe into an all-encompassing darkness, a cosmic night that never ends. Over unimaginable timescales, far beyond human comprehension, even protons, the fundamental building blocks of matter, may decay, their stability undermined by the relentless march of time, dissolving all remaining matter into a thin, ever-diluting soup of fundamental particles. Black holes, the last surviving structures in this desolate universe, will eventually evaporate, slowly but surely, through the quantum process of Hawking radiation. When the final black hole, the last vestige of structure and complexity, finally vanishes, only a cold, empty void remains, stretching out to infinity in all directions. No usable energy, no active processes, no recoverable information, just a silent, eternal night, an unending expanse of nothingness. This is the Big Freeze or heat death, not a dramatic, fiery end, filled with explosions and cataclysms, but a slow, inevitable fading away, a gradual decline into absolute zero. Time itself may lose all meaning, becoming irrelevant in the face of such utter stagnation, in this final, frozen state, the ultimate expression of cosmic entropy. The universe's story, once filled with vibrant activity and boundless potential, ends not with a bang of destruction, but with a whisper of silence, a gentle fade into oblivion. An endless night, a cosmic darkness stretching on forever, an eternity of emptiness. Now let's consider a scenario that's the polar opposite of the ever-expanding universe we currently observe. Imagine the universe contracting, shrinking in on itself. This is the concept of the Big Crunch. It's a fiery, cataclysmic collapse, a cosmic implosion of unimaginable scale. If the universe's density is high enough, meaning there's enough matter packed into the cosmos, gravity could eventually halt the relentless expansion we see today and, instead, reverse it, pulling everything back together. Galaxies, once drifting apart, would rush together, drawn by the ever-increasing gravitational pull. The cosmos would begin heating up dramatically as everything contracts, the space between objects shrinking rapidly. The night sky, once a canvas of stars against darkness, would blaze with searing light, an unbearable brightness. This is because the universe grows denser and hotter with each passing moment, the energy intensifying. Stars and planets, the celestial bodies we know, would be vaporized by the extreme heat and pressure, reduced to a chaotic soup of fundamental particles, their structures completely broken down. Black holes, those cosmic vacuum cleaners, would merge, growing ever larger and more destructive. Then even they would be torn apart by the unimaginable extreme forces at play, the very fabric of space-time unraveling. In the final, fleeting moments, all matter and energy, everything that exists, would compress into a single, infinitely dense point, a singularity beyond comprehension. This is the ultimate singularity. The Big Crunch, in essence, is the Big Bang in reverse, a cosmic reset button, if you will. Could this singularity, this infinitely dense point, spark a new universe, igniting another Big Bang and beginning the cosmic cycle anew? The Big Crunch is not just an ending, it's a possible rebirth, a cosmic phoenix rising from the ashes of the old, a universe recycled time and again in an endless cycle of destruction and creation. Is this the ultimate fate of our universe, the end as we know it, or simply a new beginning in disguise? There's a third, more terrifying fate, the Big Rip. If dark energy grows stronger, it could tear the universe apart. Expansion would accelerate until it overcomes gravity, first ripping apart galaxy clusters. Galaxies themselves would be shredded, their stars flung into the void. Eventually, even solar systems would be torn apart, planets ripped from their stars. In the final moments, the Earth would be destroyed, its very atoms pulled apart. The forces binding molecules and nuclei would fail. In a fraction of a second, every particle would be isolated, unable to interact. The fabric of space-time itself would be torn asunder. The Big Rip is a sudden, violent end. Everything, everywhere destroyed. No structure, no matter, no space-time. The universe unravels completely. The end, in a final, definitive rip. What if the universe doesn't slowly wind down or meet its end in a fiery, violent collapse? What if instead, the end is abrupt, unexpected, and absolute? What if it all ends in an instant? Enter vacuum decay, a theoretical yet terrifying possibility that lurks in the shadows of our understanding of the cosmos. It's a sudden quantum catastrophe, a game changer on a scale we can barely comprehend. The unsettling truth is, our universe may not be as stable as we think. It may exist in what's called a false vacuum, a precarious state, like a house of cards on the verge of collapse. Imagine a lower energy, more stable, true vacuum exists, a state our universe could potentially transition to. Then, a random quantum event, a tiny fluctuation in the fabric of reality, could trigger the formation of a bubble of this new, true vacuum reality. And here's where it gets truly terrifying. This bubble would expand outwards, in all directions, at the speed of light, rewriting the fundamental laws of physics as it goes, leaving nothing untouched in its wake. No warning, no escape, utterly unavoidable. Everything in its path, every atom, every particle, would be instantly obliterated and replaced by entirely new physics, a new set of rules governing existence. Planets, our cosmic homes, stars, the beacons of light in the vast darkness, galaxies, gone in a blink as if they never existed. It's not an explosion in the traditional sense, but a fundamental phase transition of reality itself, a shift in the very essence of what is. The most chilling part of this cosmic horror story? It could happen at any moment without warning and we'd never see it coming, never even know what hit us. The universe erased from existence, replaced by something utterly alien, something beyond our current comprehension. Vacuum decay is the ultimate cosmic blindside, the universe's version of a rug pull, a sudden, silent end to everything we know and understand. Reality rewritten in an instant, leaving no trace of what came before. Let's revisit the Big Freeze through the lens of thermodynamics. The second law of thermodynamics says entropy, disorder, always increases. The universe is heading toward maximum entropy, perfect equilibrium. Energy spreads out, becoming less useful until no work can be done. Stars burn out, black holes evaporate, and all energy gradients vanish. The cosmos becomes a uniform, cold soup of particles. No temperature differences, no motion, no events, just stillness. Time itself may lose meaning as nothing ever happens again. This is heat death, not a violent end, but eternal stasis. The universe's story concludes in perfect, everlasting quiet. All energy spent, all processes ceased. The final equilibrium, an unchanging, silent void, the ultimate peaceful end. From the slow chill of the Big Freeze to the sudden shock of vacuum decay, the universe's possible endings are as humbling as they are awe-inspiring. These theories remind us that the cosmos is dynamic, finite, and mortal. Yet our ability to contemplate these fates is a testament to human curiosity. We are the universe's way of knowing itself, even as we ponder its end. Which theory do you find most compelling or frightening? Share your thoughts below. Thanks for joining this journey to the end of time. Like and subscribe for more cosmic explorations. Until next time, keep looking up.
The universe is a vast, dark ocean, dotted with islands of light, galaxies, stars, and planets. Yet beyond these familiar shores, the cosmos hides deeper mysteries. Among the strangest is the concept of a white hole. We know black holes, regions where gravity traps everything, even light. But what if the universe has an opposite, a place where nothing can enter, only escape? This is the white hole, a theoretical fountain of matter and energy, forever expelling, never consuming. Unlike black holes, which imprison, white holes repel. They exist as mathematical solutions in Einstein's equations, haunting the edge of our understanding. Imagine a cosmic spring, wound tight, suddenly releasing its energy outward. If real white holes would rewrite our ideas about beginnings and endings in the universe, To understand them, we must push the limits of physics, grappling with gravity, singularities, and the birth of the cosmos. The story of white holes is not just about strange objects, but about our relentless quest to understand the universe. Each new mystery is an invitation to wonder. The white hole is one of the universe's most profound riddles. It challenges us to read deeper into the cosmic book, and so our journey begins. To grasp white holes, start with their twin, the black hole. Black holes are cosmic traps, regions where gravity is so strong nothing escapes past the event horizon. Now, reverse time. Imagine matter and energy erupting outward from a singularity never to return. That's a white hole, a one-way door but leading out. Nothing can enter, everything is expelled. White holes and black holes are mathematical opposites, both born from Einstein's equations. One devours, the other gives. If you approached a white hole, you'd be pushed away by an overwhelming force. From afar, it would shine blindingly bright, constantly emitting matter and radiation. But its event horizon is impenetrable. No entry, only exit. White holes are fortresses forever expelling their secrets. They are the ultimate cosmic source, while black holes are the ultimate sink, two sides of the same cosmic coin. White holes emerge from Einstein's general relativity, the same theory that predicts black holes. The Schwarzschild solution describes both. A black hole's event horizon traps, a white hole's expels. For a white hole, the event horizon is a one-way surface. Matter and light can only leave, never return. At its heart is a singularity, but unlike a black hole's future singularity, a white hole's is in the past. All its matter and energy erupt from this single point. But where did it come from? The math says it was always there, a troubling idea for physicists. The biggest problem, stability. Even a single photon approaching a white hole would trigger its collapse into a black hole. This instability makes white holes unlikely to exist in our universe. Despite being mathematically possible, they seem physically forbidden. White holes remain theoretical, their existence challenged by the laws of nature, yet they push us to question what's truly possible. If white holes exist, they should be spectacular explosions of matter and energy. Some once thought quasars or gamma-ray bursts might be white holes. But we now know quasars are powered by supermassive black holes, and gamma-ray bursts come from collapsing stars or neutron-star collisions. A 2006 gamma-ray burst sparked speculation, but no conclusive link to white holes was found. Every strange cosmic signal has found a conventional explanation. Today, there is zero direct evidence for white holes. We photographed black holes and detected their gravitational waves. But white holes remain mathematical phantoms. They haunt our equations, but not our telescopes. The search continues, but so far white holes are only beautiful ideas. Why haven't we found white holes? The answer lies in physics. Black holes form naturally from collapsing stars, a one-way process. But a white hole would require the universe to run backward, violating the second law of thermodynamics. Entropy always increases. Shattered glass doesn't reassemble, and stars don't unburn. A white hole would mean a spontaneous decrease in entropy, something nature forbids. Even if one formed, it would be instantly destabilized by incoming energy, collapsing into a black hole. The universe seems to prevent white holes from existing. Some speculate white holes might have existed only at the universe's birth. Perhaps the Big Bang itself was a kind of white hole, a single eruption of everything. In this view, we live inside the aftermath of the only white hole that ever mattered. White holes may be relics of cosmic origins, not objects scattered across the sky. Their mystery connects to the deepest questions of where we come from and why the universe is the way it is. If white holes are so unlikely, why study them? Because their existence in Einstein's equations shows our understanding is incomplete. White holes force us to confront the clash between general relativity and quantum mechanics. At their core lies a singularity where physics breaks down. Some theories suggest black holes might bounce and become white holes, connecting universes or forming wormholes. These ideas, though speculative, push the boundaries of science and imagination. Studying white holes tests our theories to the limit. We must either explain why they can't exist or search for evidence. This process is the heart of science. Even if white holes are fantasy, the quest to understand them teaches us about the universe. Our journey has taken us from black holes to their mysterious opposites. White holes remain mathematical possibilities, but nature seems to forbid them. Every cosmic mystery once linked to white holes has found a simpler explanation. Yet the questions they raise about time, entropy, and the universe's birth remain profound. Perhaps black holes are not endpoints, but beginnings. Perhaps information is not lost, but reborn. White holes challenge us to imagine, to calculate, to search. They remind us that the universe's map is still unfinished. Our curiosity drives us to explore even the impossible. The greatest discoveries may still lie in the blank spaces of our cosmic story.